All right, so welcome to the last week. You've survived. Sort of, intact, slightly. Yeah. Oh, by the way, I didn't mark Joe out. Joe's here, right? Joe is here. And Joe didn't get his test back. Oh, here you go, 92. Anybody else I missed? I think that's it, right? Everyone's taking makeup? Good, all right. All right, so what's a vector? All right, kindly consider the following. Let's say you're taking a stroll. You take a stroll in the summer along the beach with the sand in your toes, right? No? Let's say you're taking a stroll and you go, I don't know, let's say 5 miles east. There's a vector. Done. Go home. We're done. That's it. That's a vector. Now, what's a vector? A vector is something which we associate with it not just a number, a quantity, like we do any other variable in this class, right? But a direction. All right. So this is what's called a displacement vector. So you know where your starting point is. Let's say, whatever that point is. And if I say I'm going 5 miles east, you know what that means, right? I'm going east 5 miles. This is not tough. But that's what a vector is. Something with a direction, something with a magnitude. Something with a direction, something with a size, a number attached to it, okay? So in this case, let's say that's 5 miles. Oops. Okay? So there's 5 miles. Then I decide to change direction and go northeast 3 miles. So let's say that's 3 miles. Hey. Okay. So what's my total displacement? How far did I walk? 8 miles, right? But what's my net displacement? How far did I get from my starting point? I'm not 8 miles away from where I started. I'm this far away. Right? That is my net displacement vector. Okay? Well, is this Pythagorean? No, because there's no right angle. Yeah, that's a problem. But if you don't have Pythagoras, you can do law of cosines. Right, okay. So can we figure out how far I really went? Let's call that x. What's the magnitude of that vector? And what is that angle? What is the direction of that vector? So notice vectors are really stated very naturally in polar form. There's an angle. The direction is an angle with the horizontal, right? And the magnitude, the length of the vector is the r. Remember the r cosine theta, r sine theta, that stuff from polar? We're going to be doing the same stuff here. All right, so can you figure out x and can you figure out theta? Let's say theta is there. That's my theta. Okay? So how do you figure out x? Well, you said law of cosines, right? So I'll start you off. X squared equals 5 squared. Okay, 5 squared plus what? Remember law of cosines? 3 squared. Then what? Minus 2 times 5 times 3 times the cosine of the angle in between. Let's see here. Hang on. Yeah, I wrote that wrong. Hang on. Back up. Back up a little bit. Okay. I just need a little more room. X squared equals 5 squared plus 3 squared minus 2 times 5 times 3 times what? Yeah, but now remember that this side is related to this angle. Do you know this angle? I'm not talking about that angle. I'm talking about this angle. I told you that angle, didn't I? Didn't I? I said I was going east, and then I started going northeast. So what's that angle? You know what northeast means? If east means, right, you're going 45 degrees. So if this is 45 degrees here, this is 45. What's the angle in the triangle? That's what I need. From 180 is 135. Ah, okay, so 135. All right, so I need the cosine of 135. Now, do you know the cosine of 135? No, really? The cosine of 135 is the same as the cosine of 45, except it's in the second quadrant, right? Think about it. Here's you're the unit circle, right? This is 0 degrees. This is 45 degrees. This is 180 degrees. This is 135 degrees. Isn't that the same angle from the x-axis? So if you know the cosine, what is the cosine of 45? The cosine of 0 is 1. The cosine of 90 is 0. But the cosine of 45, rad 2. It's rad 1/2. Rad 2 over 2, right? That's the, now remember, is it the x or the y coordinate of this point? It's the x. All right, so now give me this x coordinate over here. Same angle, but is it the same x? It's negative rad 2 over 2. Perfect. Okay. So let's write that out. So x squared is 25 plus 9 minus what, 30? And times negative rad 2 over 2? So what happens with that negative? Becomes a positive, because it's negative 30 times a negative rad 2 over 2, so it's positive. So I'm really adding in this case instead of subtracting. And what about the 2? The 2 goes into 30 15 times. So this is going to be, let's see, 25 and 9 is what, 34? Plus 15 rad 2. Okay? And how much is that? Well, let's find out. Let's ask Siggy. What is 34 plus 15 rad 2? You get about 55.213. Alrighty. So we're going to say that's about 55.213. All right, so now we have that answer. Now, that's going to be, that's your x squared. I want the length of the vector, the magnitude of the net displacement, right, is x, not x squared. I got x squared. What's x? Square root that. Oh, okay. So square root that, and let's see what that is. Let's say x then is about, let's take the calculator. Let's do the square root of the answer we just had, and that's about 7.431. Okay? Okay, so it's 7.431. And are there units in this? X is in what? Miles. Right? So you physically walked 5 miles east and 3 miles northeast. You actually took an 8-mile stroll. But you're really only 7.4 miles away from where you started. As the crow flies, a beeline, as a bee flies, right? You ever hear that, beeline? How a bee flies? Okay. All right. So, now, what else? Well, what about this angle in here? Can I uniquely specify this net displacement? It's a vector. It's got a direction and it's got a magnitude. We've got the magnitude, 7.4 something, right? Can we get that angle? Do we have enough information to get that angle? Now remember, we have x. We know x is exactly, what was it, 34 plus 15 rad 2? I don't want to have round off error, so I'm going to say, and then square root it, what? And then law of sines will give me the angle, right? So it's 34 plus 15 rad 2 was x squared. When we square rooted it, we got the 7.4 miles, right? Now that's an exact amount for x, so I don't have round off error later when I'm trying to get the angle. So how do you get this angle? Well, we use the law of sines to get the side, because we had side angle side, right? We had this side with this angle this side. How do you suppose you're going to get the angle? Law of sines. So the sine of theta is 2. Remember, we have to do an angle side pair, right? So the sine of theta is to 3. As the sine of what other angle do we have? 135 is to this crazy value for x, right? All right, let's write that. Let's do it on the next page. So the sine of theta, the direction of the net displacement, is to 3 as the sine of 135 is to x, which was rad 34 plus 15 rad 2. So how do you get theta? How do you get sine alone? Let's start there. Cross multiply. Well, you don't even have to cross multiply. All you have to do is multiply by. All you have to get rid of is the 3. So multiply by 3, and then you have sine of theta is that. How do you get theta? Inverse sine. Okay, so theta is the inverse sine of this whole mess times 3. 3 times the sine, of 135 degrees over rad 34 plus 15 rad 2. And let's figure out, now that's an exact number, but who knows how big that is. Let's get a decimal equivalent for that. So what is 3 sine of 135 divided by, well, let's write it out, the square root of 34 plus 15 rad 2. Now here's the rad 2, close the rad, close the other rad, and there you go. Now that's what we're taking the arc sine of. So second sine of that answer is 0.036. I think I'm in radian mode. What mode is this? Radian mode. Well, for some reason we've been talking today in degrees, so why don't we do this in degrees? All right, so this is what I'm going to do. I'm going to do this, but I'm going to put the arc sine in front of it. Second insert second sine, then close the parenthesis at the end for the arc sine. Change the mode to degree if you want degrees. And that 0.036 radians is about 16 degrees. So 16.588 degrees. Okay? So let's do that. 16, so theta is about 16.588 degrees. There's a decimal there, and that's not a theta. Okay, that's not a theta either, but all right. Close enough. Alrighty, so there you go. So, a vector is a quantity that has a magnitude, a certain number associated with it, a size, right, and a direction. It's sort of like polar mode, r theta. It's r theta all over again, right? It's coming back to haunt you. Okay. All right, now why do we use vectors? We use vectors to not only to symbolize displacement, a direction and a distance, right, but velocity, how fast you're going, in what direction you're going, acceleration, force. You could use vectors to model things in economics and population. We'll talk about that too. You can talk about, they use vector analysis a lot in games. You ever play a video game with a lot of graphics going on, a lot of video, a lot of things flying around and falling and crashing and burning? Well, it couldn't do that without tons and tons of vectors calculations, okay? Vector calculations is dealing with current displacement, current velocity, current acceleration, stuff like that, to make it look realistic, All righty. So, all right, let's try that again. Let's say, let's try another example. Let's say you have a spacecraft. Okay? And the spacecraft is being acted on by two forces, by two gravitational fields. One from Jupiter. Ew, what happened to my geometry? And one from Mars. All right. Now, let's say that, all right, so this is a vector pulling the satellite, let's say, in this direction. And here's a vector pulling the satellite in that direction. So the force vector is like pulling. It's talking about how much it's being pulled in a certain direction. Let's say this pull has a magnitude of 8 units, 8, newtons. And this one has a magnitude of 3. And this angle here is 70 degrees. the resultant vector? What do those two pulls actually work out to be? What is the sum of those two vectors? So if I call this vector u and this vector v, I want u plus v. And it's the same idea, yeah, exactly. All right, so now the thing is, have you ever dealt with vectors before? Have you heard about the resultant vector? Right, have you heard of the law of the parallelogram? When you add two vectors, you get basically what we got here. Didn't we get that here? We basically added this vector to this vector, and we got that vector. But can you envision a parallelogram inside which all of this occurs? Right? If you take this side and draw it up here, and you take this side and you draw it over here, don't you get a parallelogram? And the resultant vector, the sum of the two vectors, is the diagonal of the parallelogram? Okay. So, how do I get the resultant here? Well, these are force vectors. These are vectors. Vectors can be anchored anywhere. Displacement vectors, they start at a certain position. But force vectors, velocity vectors, you can put them wherever the heck you want. So it's acting on the satellite here. But I could draw it out here instead and look at the diagonal. Right? I could say, do this. Look, let's draw it. Let's draw this parallelogram. Pretend it's parallel. Ugh. Okay? So if this is 70, what's that? If angle A is 70, what's angle B? 110, right? Remember that when parallel lines are cut by a transversal, the interior angles formed are supplements. When two parallel lines are cut by a transversal, the alternate interior angles are congruent, that kind of stuff. All right, so if I have, so if that's 70 and that's 110, what's that? What's angle C? 70, and what's angle D? 110, okay. So can I talk about this diagonal? Ugh. Ow. Okay. All right, so here's the force vector from Jupiter. Here's the force vector from Mars, but I want the net force, the sum of the two forces. This guy, all right? So I have vector AB is the force from Jupiter. Vector BC is the force from Mars, but I want the vector AC, all right? So now remember, this is 8, this is 3, whatever the units are, newtons or something. This, you just told me, is 110 degrees, right? So can you figure out the net force? Let me call that x. And isn't this the law of cosines all over again, right? Isn't it the same thing? Because you have a side, angle side. So since this is 3, this is 3, law of parallelograms. Since this is 8, this is 8, right? You can draw the 110 here, the 110 here, the 70 here, the 70 here, whatever you need to do. All right. So you tell me, how do I get x squared? X squared is going to be what? 8 squared plus 3 squared minus 2 times 8 times 3 times cosine of 110. Perfect. And think about it. 110 is in the second quadrant, so the cosine of 110 is going to be negative again. So we're really not subtracting here. It's not really a negative 2 times 8 times 3, right? It's really adding. So let's work this out. Now this one we can't do exactly. Last time we had a reference angle, 45 degrees or 135 degrees. We could write this exactly. I can't write this exactly. So the best I'm going to get is that x is the square root of 64 plus 9. What's 64 plus 9? 73? Okay, so 73 minus 2 times 8 times 3. What's that going to be? What's 2 times 8 times 3? 48? 48. The cosine of 110, but again, cosine of 110 is negative, so we're really not subtracting here. So x is the square root of that, and let's see what that is. All right, that's going to be approximately, whoops, why is that doing that? Okay, get rid of that. What is that? It's going to be approximately, put a little dot up here, huh? Okay. what? Well, let's see. On the calculator, it's 73 minus 48 cosine 110. Now, I'm in degree mode, right? Okay, so I can use the cosine 110. Square root of 73 minus 48 times the cosine of 110. And you get 9.456 units, whatever they are. Usually a unit of force is in newtons, so some multiple of newtons. It may not be just newtons, it might be like, I don't know, meganewtons or something, but 9.456, okay? So 9.456. They didn't give a unit, so don't worry about that, but something like newtons, okay? Can you figure out the angle? Every vector has a magnitude and a direction. So we got the magnitude, 9.4 some odd newtons. But I also want to know what this angle is. Where is it? This angle here. I want this theta. And just like last time, you can use law of sines, can't you? So the sine of theta is to sine of theta over 3 as sine of 110 is to what we just calculated, right? And again, don't use the rounded off value, use the exact value. So when you round off for the theta, it's not too bad, okay? All right, so let's write that. Let's write that one down. We've got the sine of theta is to 3 as the sine of 110 degrees is to the square root of 73 minus 48 cosine 110. That's a cosine. Yeah. Well, you can find any one of these angles, but I'm talking about the angle that it's making with the trajectory. Which angle did you want? CAD. That one. Well, only because originally, all right, well, this is how I'm thinking about it. I'm thinking that the satellite is trying to go to Jupiter, but it's taking off course by Mars. So I want to know how far off course I am. I should have said that. That's what I'm looking for. I should have specified which angle I want. All right, so did we get the angle? No, but we're going to do it by multiplying by 3 and arc sine again, right? So theta is the arc sine of 3 times the sine of 110 over rad 73 minus 48 cosine of 110. All of that. And so let's do that. And let's see how many degrees that is. I'm in degree mode today for whatever reason. All right, what is this? Okay, get rid of that. Okay. And get back to there, and get back to there. Okay, so it's the arc sine of 3 times the sine of 110 divided by the square root of 73 minus 48 cosine of 110. I'm going to close the cosine, I'm going to close the denominator, I'm going to close the arc sine, and I'm going to get about 17.345 degrees. All right, is everyone okay how we got that? 17.345 degrees? So that's about 17.345 degrees. All right. And again, what does that mean? That means that if AB is the direction I'm trying to go in, I'm trying to go to Jupiter, let's say. This satellite is trying to go to Jupiter. But Mars is pulling it off course. How far off course are we going? We're going 17 degrees off course, roughly, right? And we're not going at the force to Jupiter is 8 units, but we're really experiencing a force of, what was it, 9.4 units, okay? All right, so that's how you add vectors. Now, we're talking about adding vectors in polar form, dealing with their magnitudes and the angles and stuff like that, but you don't have to do that. All right, how about this? What about subtracting vectors? What if, whoops, where am I? What if now I take, um, so now what I want to do is I want to fix the course. I want to say, okay, this satellite has an engine on it, and I could fire it in any direction I feel like for 4 units of force, whatever the units are, say newtons, because that's a common unit of force, right? All right, so I want the spacecraft to get back on course. I want it to go that way. All right, I want to go back toward Jupiter. All right, but remember, we're going this way at a certain magnitude, let's say roughly, what was it, 9.456 units of force in that direction. Okay? And the angle here is, what was it, 17.345 degrees, right? (17.345 degrees). What I want to know is, what is this vector? I want to end up going this way, right? I want to go toward Jupiter. Let's say this is toward Jupiter. I'm going this way. I want to fix my course. All right? So what is that angle? What is that vector? All right? Now what I'm really saying is, here's the spacecraft. It's being pulled this way, a net force due to Mars and Jupiter. I want to pull it this way, a certain angle and a certain magnitude to fix my course. But I'm drawing it here to make it easy. All right? You can take the vector with the same angle, the same magnitude, put it wherever you want, and it's still valid, okay? So I didn't make it long enough, though. Make it a little bit longer. It's this, I'm trying to draw this vector over here. Whoa, that's bad. It was so bad. All right, long enough. Say that vector. So say this vector and this vector is the same vector, okay? So this is the net force due to Jupiter and Mars. This is the angle that the force is working on. It's taking me off course. I need to figure out what this angle is and what this magnitude is. So let's call this, I don't know, let's call this R and theta. For the force due to the engine on the satellite, trying to correct the course, right? So technically, it's sort of like we're subtracting, but all right, let's not talk about that. All right, so let's say, what do I want to do? Hang on. All right, so this I know. I know the force that the engine can generate. It's 4 units. That's given. Say that's given. Can you figure out what this theta is? How do you figure out this theta? I know the force that the engine can generate. I need to know which way to aim it, right? Which direction to shoot that engine so that I get back on course. So I get back on, let's say this course A to B is toward Jupiter. Okay? How do I figure out that angle? Well, I got this triangle here, ABC, let's say, right? This triangle ABC. Isn't theta in there somewhere? Isn't theta also in the triangle?
Yeah.
When 2 parallel lines, aren't these parallel lines because it's the same theta? If 2 parallel lines are cut by transversal, the alternate interior angles formed are congruent, right? So this is theta also. So can I use law of sines to figure out theta again? Realizing that this is still 4. Right, so I've got this side, I got this side, I got this angle. Can I get that angle? Let's see, sine of theta is to that side, as the sine of 17.345 is to that side. We could do it, right? And in fact, we could also do the law of cosines to figure out the net force that the satellite is experiencing, because not only is it experiencing the force due to Mars and Jupiter, but now due to the engine. So what is the total force toward Jupiter? We could figure that out too. Let's call that x. All right, so how do you figure out theta? That's the first question. You tell me. Sine of theta is to 9 point, yeah, but it's not 9 point whatever, because that's round off error, right? It should really be, where did we get the 9 point whatever? Not there. There. It's a square root of 73 minus 48 cosine of 110. You know what I should do? Is I should store these values. Let me store this somewhere in the calculator. Let me call this A, and I'm going to call this B, just to store it somewhere. So I don't have round off error. I have all the decimals I need, right? All right, so let's go back to Ziggy. Let's go back to the, all right, this guy, this is the angle, right? This is that angle here, right? So why don't we store that somewhere? Let me call that, I'm going to say store as alpha B for the angle. And I'm going to say store as alpha A, that magnitude, the 9.4, and that's from here, isn't it? Yes, it is. So store that as alpha A. So that I don't have to write that humongous thing out, I can just say A when I need it, okay? So I'm going to say that that's A in the calculator. Okay, I'm going to write it out. I'm going to say it's 9.456, right? But that's rounded off. I'm going to use A in the calculator, it has more decimals, right? Is to the sine of that, okay, is to the sine of 17.345. But again, I stored that angle as B, so I don't have round off error. Or I don't have to type out that whole huge mess that gave me the 17.4. I could do that there too. Over, all right, the sine of that is to 4, right? So how to get the theta of the engine? The direction that you have to aim that 4 Newton engine. Cross multiply, or in fact, simply do multiply by the 9.4 and arc sine, right? So theta, that's not a theta. Theta is the arc sine of 9.456 times the sine of 17.345 degrees all over 4. All right, that's the sine of theta. I should say I want the arc sine. So let's make some room here. Oh, it is the arc sine. Whoops, wait. I didn't write it. Arc sine. It's the arc sine of 9.4 whatever times this, right? So let's do that. So this doesn't go out here like this. Ding. Okay. All right, now remember that that's A and that's B. So when I go on the calculator, I'm going to say the arc sine. Whoops. What did I do? Store as alpha A, enter. All right, so alpha A is that, and alpha B is the angle? It is, okay. So here's what I'm going to write. I'm going to say second sine of alpha A times the sine of alpha B, all right, divided by 4, and you get 44.811 degrees roughly, okay? So let's see, so that's about 44.810 degrees. All right, good. And likewise, we could figure out the net force due to all this pulling. We're pulling by Jupiter, we're pulling by Mars, and we're pushing. We're actually, it's sort of a negative force for the engines to get you back to where you were, right? How do you get that net force? Law of cosines. X squared is, right, 4 squared plus this thing squared minus 2 times 4 times this times the cosine of this angle. How would you get this cosine? How would you get this angle? Subtract, right. So subtract the 17.344 and the 44.811 from 180, and you could do that. But I spent way too long on this, so I'm going to move on. All right, so that's section 12.1. It's a lot of loss signs and log cosines, basically, right? When you deal with vectors in polar form, the magnitude and the angle, it's like an r and a theta, like in polar form, you're doing a lot of loss signs, a lot of log cosines, basically, that's it, okay? All right, so now, is there another way to deal with vectors? Yes, there is. You can do it now. Remember, we had a way of converting from r theta to x and y, right? What if we talk about the horizontal and vertical components of the vector instead? That makes life even easier, I think. All right, so this is section 12.2. Let's say you have, let's see. All right, let's say you have okay, you're on a ship, and this is your displacement vector. Okay? Now, you think, according to your compass, that you're going 200 miles due east. But then, once you've done the 200 miles, you figured out that your stupid compass was broken. And you really weren't going due east. You were going 17 degrees north of east. 17.4 degrees north of east, let's say. So instead of going 200 miles east, you're off track. This is still 200. You did go 200 miles, but you went 200 miles in the wrong direction. So this is a displacement vector. I want the horizontal and vertical components of that vector. That's what I want. I want to know what's x and what's y if you talk about Cartesian components. All right, so we got the r and we got the theta. How do you get the x and the y? Think polar. How do you get x? R cosine theta. How do you get y? R sine theta. That's it. Okay. So what is x? It's going to be r, which is how big? What's the magnitude of your displacement? 200 miles, right? So 200 cosine of the angle, which was 17.4 degrees. Okay. And then what's y? The same thing but sine. Okay, so y is 200 times the sine of 17.4 degrees. Okay, good. Now let's get a decimal equivalent and see what that is. All right, so now we're talking about the horizontal and vertical components. So instead of saying, okay, go 17 degrees this way and go 200 miles, instead you're going to go a certain distance in x and a certain distance in y and get to the same place. Right? All right, so what is x about? Okay, x is about, let's see, you did it already? All right, on the calculator, was it 200 cosine 17? Okay, 200 cosine 17.4 is 190. Is that what you got? 190.848? Okay, so 190.848. Ugh, that's an 8. There's a point here. And to get the vertical component, it's real easy. Second enter, and just make this a sign. 59.808? Yep. 59.808. So, what does that mean? Instead of going 200 miles east, you went 190 miles east and 59 miles north. You're off track, almost 60 miles north, off course. What the heck? That's way off. But the point is this. I can specify this vector now this way. I could say that vector is the same thing as saying, let's see, how about my displacement vector? For some reason they use S a lot for displacement. My displacement vector is the x component, which was 190.848, 190.848 in the x direction. Let's call that vector I. What? Have you seen this kind of notation? Plus, and it's about, right? This is approximate. Plus, what was it? 59.808? 59.808 J. What is J and what is I? Have you seen this notation before? Okay. I is a unit vector. In fact, very often they don't use an arrow on top to denote a vector. They use a caret or a hat on top to denote a special kind of vector called a unit vector. And likewise here, which means it's a vector going in a certain direction, but it has only a length of 1. So if you think of I as a unit vector pointing in the x direction, and j as a unit vector pointing in the y direction, this means go 190 miles in the I direction, in the x direction, right? So it's 190 times I, but I is 1 unit long. The only thing that really gives you is a direction. So 190 times 1 is still 190, go in the x direction. And 59 times j is still 59 times 1, but in the y direction, in the positive y direction. And if you go into 3 dimensions, you're going to talk about I, j, k. I is a unit vector along the positive x, j is the unit vector along the positive y, and I, j, and the k is the unit vector along z. Have you ever heard of the right-hand rule? Okay, good. That's, yeah. Oops, what happened here? I lost my connection. Okay, we're back. Alrighty. So there you go. All right, so it's actually very convenient to talk about the horizontal and vertical components of a vector. Okay. Let's say, for example, let's say I gave you these vectors. Let's say I gave you the vector u. And it's 5 units in the positive x direction plus 7 units, well, plus 7 units in the positive j direction. All right, let's say I gave you another vector, v. And it's just 1 unit in the I direction and 1 unit in the j direction. Okay. And my question is, what is, okay, let's just talk. How do you add vectors? How do you subtract vectors? So what's u plus v? Component-wise. Now, we're not doing r theta now. We're doing x's and y's. And it's very easy. To add vectors component-wise, you add up the i's, you add up the j's. So how many i's do you see? 6. But I'm losing my connection to the splash top here. What happened here? I'm losing my Wi-Fi, sorry. Hang on, I'm reconnecting. Come on, Wi-Fi, reconnect. What is going on? That should connect. It is connected, right? Okay. Okay, good. All right, so you get 6 i's plus 8 j's. That's it, simple. So now adding and subtracting is very easy. Before, the adding and the subtracting had to do with law of sines, law of cosines, right? It's a big mess. All right, what if I subtracted? What's u minus v then? What's u minus v? Exactly, it would be 4i plus 6j. Now, why don't we graph that? Let's see what that means. I'm going to graph u is 5, 7, and v is 1, 1, right? Okay. So let's graph that. All right, so 5, 7 is, say, 1, 2, 3, 4, 5 is here. And 7 is 1, 2, 3, 4, 5, 6, 7. Whoops, not quite to scale, but you get the idea. So the vector starts here and ends here. That's what that looks like. Okay, roughly. Okay? Now, what was the other vector? It was 1, 1, right? 1i, 1j. All right, so that goes up 1, over 1. This is not drawn to scale, is it? That's a problem. Up 1 over 1, let's say, is here. Ugh, I don't know if I like that. So that vector looks like that. Okay, let's say. But look at the answer. The answer was what? Whoops, where'd it go? The answer when we added was 6i 8j, right? What does 6i 8j look like? Yeah, this is not drawn correctly. Wait, I got to do this better. Yeah, I is horizontal. Yeah, I don't like how this works out. Hang on. Let me try this again. All right, I got to be more precise, okay? So here's 5. 1, 2, 3, 4, 5. Here's 7. 1, 2, 3, 4. Wait a minute. I could do this easier. Why do I have to make this so tough? Wait, hang on. View, journal, paper, style, graph. Ha! There you go. Yeah. Okay. So let's say this is the origin. Where's 5, 7? 1, 2, 3, 4, 5 is here. 1, 2, 3, 4, 5, 6, 7 is here. So that's the end of the vector. So it goes from here to there, right? So let's see if we can draw that. Yeah. Where's my vector going away? I'm getting rid of the wrong thing. Go away. Okay. View. Style. No, journal style graph. There it is. Okay. All right. So I'm starting here, and I'm going over 5. 1, 2, 3, 4, 5, up 7. 1, 2, 3, 4, 5, 6, 7. I'm going there, right? Now, can I just draw this vector already? Why isn't it doing it? There you go. Okay, so there's a vector. That's u. Now, where's the vector 1, 1? It's here. Ugh. But look at the answer. The answer was what? What was it? 6, 8? Okay, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8 is here. You know, I'm sorry, this is not a good example. I'm trying to show you that when you add two vectors, you're getting that diagonal thing. But these numbers are not easy to draw. Let's make an easier example. What if I said I take the vector 3, 4, this vector right here. I'm going to give you a whole different example, okay? That vector, 3, 4. And I add to it, let's say 1, 2, 3, 4, 5, 6, 1. This vector. Okay? So this is the vector 3, 4. And notice you can use what we usually look at as coordinates. We can use that for vector notation. And 7, 1. Now let's say I added those two instead. Let's say we add those two. So add 3, 4, and 7, 1. What do you get? 10, 5. Okay, so let's graph 10, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5 would be 1, 2, 3, 4, 5 is here. So that vector there. Now, does that make it more obvious? That the sum of two vectors is the diagonal of the parallelogram that those vectors define? So if you take this side and draw it over here, and you take this side and you draw it up here, you have a big fat parallelogram, and the resultant vector, the sum of two vectors, is the diagonal. Okay, that's what I was trying to get at. So this is another way to notate vectors. What was it, 10, 5? You can actually use like the XY notation that we use for coordinates, but realize that it really means 10i plus 5j. All right? So if u is 3, 4, and v is 7, 1, then the sum is this 10, 5 is u plus v. Now, while we're at it, how do you suppose you subtract vectors? How do you subtract 3, 4, and 10 and 7, 1? Let's say 7, 1 minus 3, 4. How about that? What's 7, 1 minus 3, 4? 4, negative 3. All right, so let's do 4. 1, 2, 3, 4, negative 3. 1, 2, 3 is down here. This is what I'm going to call V. Well, wait. It was, what was it? It was 4, negative 3, right? 4, negative 3. That's what I'm going to call V minus U. But where's the parallelogram? Remember what we said. How do you subtract? You never do. You add the opposite. So instead of subtracting V minus U, I'm going to add V plus negative U. What do you think negative U is? If U is 3, 4, negative U is negative 3, negative 4. So if I draw that, let's see, one from the origin, 1, 2, 3 to the left, and 1, 2, 3, 4 down is this vector here. Let's say that's negative U. So is it true that this is the diagonal of this parallelogram? Should I make it red? Let's make it red. How? All right, so think of a parallelogram made up of those two red sides. Is that the diagonal? So to subtract V minus U, I'm really adding V and negative U. So still adding, it's still a resultant, it's still a law of the parallelograms. All right, where the parallelogram is out here. Oops. Why can't I do this straight? Ouch. I can't do this straight. And out here. Let's say. Okay, so you see the parallelogram? So if the sides are V and negative U, the sum, the diagonal of the red parallelogram is the difference, V plus a negative U or V minus U. All right. So it's very easy to add vectors component-wise. Just add the horizontal parts and add the vertical parts. It's very easy to subtract them component-wise. Subtract the horizontal parts, subtract the vertical parts. Easy, not a big deal. So then, what do you suppose this means? What would this be? If U is still, what was U? 5, 7 from the original problem. Remember, I wrote it 5i plus 7j, but now I'm writing it this way. And V is still 1, 1. What do you suppose U minus 3V is? What's U minus 3V? Now, we've talked about adding and subtracting vectors component-wise, but we didn't talk about dilating. That 3 is a dilation. So if V is 1, 1, what do you think 3V is? 3, 3, that's it, okay. So it's the same thing as saying U, which is 5, 7, plus 3 times V, which is 1, 1, but 3 times V is going to be 3, 3. So you got 5, 7 plus 3, 3 is going to be what? What do you get? 8? Oh, it's minus, sorry. We're talking about subtracting here, right? So minus. So U minus 3V is 5, 7 minus 3, 3 is what? 2, 4? Is that, did I hear it? 2, 4? Okay. There you go. Alrighty. So, okay, what if, all right, let me try this. Everyone okay with this? You got this? All right. What if I define my vectors by their endpoints? What if I say one endpoint is at negative 3, 1? So if this is the origin, negative 3, 1, 1, 2, 3 is here. So let's say the point P is at negative 3, 1. And this is just the origin. Okay? And the point Q is at 2, 4. So over 2, up 4. So Q is at 2, 4. And let's say that defines the vector PQ. Yeah. So let's say that V, the vector V, is the vector that starts at P and goes to Q. What are the components? That's my question. Isn't it easy? How do you get from P to Q horizontally then vertically? How far do you go horizontally from P to Q? How far is it horizontally, this distance here, from P to Q? 5, right? All right, so isn't that just, let me make a little more room here. Isn't that the same thing as taking where you're ending up, the 2, minus where you started, the negative 3, comma. What do you think you're going to do with the y's? I did 2 minus negative 3 for the x's. What are you going to do for the y's? 4 minus 1, same thing. Because isn't 4 minus 1 3 units? Isn't that how far you're going vertically? So if you're defining your vector by the endpoints, where you start and where you end, you take your x components, subtract them. Well, how do you subtract 2 minus negative 3, by the way? You adding 3, so it's 5. So 5 units to the right, comma, and then 3 units up, which could easily be written in ij notation, if you like. That's going to be 5 i's plus 3 j's. Same thing, just different notation. Okay? You're going to see both notations flip-flop because they're synonymous anyway. Okay? Alrighty, so that's how you deal with. So 12.1 was how do you deal with vectors polar-wise. 12.2 is how to deal with vectors component-wise. Alrighty. So we've talked about adding, subtracting, dilating. All right, let's see. Let me go back to my regular paper. No, not that. Where did it go? That one? What's this one? What's this? Oh, that's what I had? Okay. That's what I had. All right. So we'll practice it up a little bit more when we go back over the homework, okay? Now, let's say, now we've been talking about two-dimensional vectors for the most part. What if you don't have a two-dimensional vector? Huh? That's the ijk. What if I have even more? What if I have 4 dimensions, 5 dimensions, 10 dimensions? Here's a 1, 2, 3, 4, 5, 6-dimensional vector. Are you ready? Okay. Let's say that the vector P has 6 dimensions. Okay? And the values in P are 3.28, comma, 1.24, comma, 6.07. Well, I'm running out of room, so let's make it 4-dimensional. One more. 1.15. Okay? Now let's say that represents the populations of several states. Let's say this is the population in Connecticut of millions of people, in Maine, in New Hampshire, and in Rhode Island. Is that right? That doesn't even sound right. Population of Maine. All right, let's say that's right. Okay. So this is Connecticut. This is Connecticut. This is Maine. This is New Hampshire. This is Rhode Island. Okay? So this particular vector represents a whole bunch of populations. Okay? Now, let's say that P is the population of each of these states in the year 1995. Let's say Q is a population vector that represents the populations of each of these same four states, but in 2005. And let's say that's 3.51, comma, 1.32, comma, 6.40, comma, and 1.31. All right? Is that visible? Do you see the decimals and everything? All right, so there's a decimal here, there's a decimal here, there's a decimal here. All right. So, for example, 3.28 is the population of Connecticut in 1995, but 3.51 is the population of Connecticut in 2005. My question to you is, what is Q minus P? What is Q minus P? How do you get it, and what does it mean? Yeah. And that'll be the quote-unquote X component, and the same thing for the Y component, and Z, right? And what does it mean, though? Those numbers you're going to get are what? How much the population changed between 1995 and 1995 and 2005. All right, so let's do that, just for fun. I mean, you can do this in your head, I guess, right? But what is 3 point? Could we? Let me think about this. Could we do this in stat edit? Let me play with this. Hang on. Can I do this? If I clear this and I clear this, can I pretend that list 1 is a vector? Let's see. Let's do this. What is 3.28? Can I do this? I'm not sure if I can do this. I'm just experimenting. And 1.24. I'm not sure if the calculator can do this vector-wise stuff. Let's just experiment. 6.07 and 1.15, right? So let's say L1 is P, the population of those four states in 1995. And L2 is Q, 3.51 and 1.32 and 6.40. That's what it was, right? 6.40 and 1.31. All right, so if I quit this, clear this, if I list L1, there's the initial populations. You can't see them all, but all right. And list L2, there's the populations 2005. What if I did L2, can I do this? L2 minus L1, I'm not sure if I can do this. Whoops, I wrote it wrong. L2 minus L1. So Q minus P. 2005 minus 1995. Is that what you would expect? Is 3.51 minus 3.28 0.23? Yep. Is 1.32 minus 1.24 Yep. Is 640 minus 0733? Yep. And I can just write arrow to get, is this 16? Yeah, there you go. Good, perfect. Now notice I don't have this in stat edit. Could I put it in L3 if I wanted to? How would I do that? Could I go up here and type it? Could I do L2 minus L1 and store in L3 on the home screen, or could I do that here? I'm not sure if I can do that here. Let me try this. Second L2 minus second L1. Can I do it here? I'm not sure about that. I could. There it is. Perfect. All right, so there it is. Or you could have just done this. Take that answer and store it as L3. I'm going to store it as L4 so you can see that it works. So stat edit. So notice that L4 is the same. So you could have done it from the home screen too. All right, so what does that mean? 0.23 means what, for example, in the context of this problem? We subtracted the population from 2005, which was L2, minus population 1995, which is L1, and 0.23 means what? The increase in the population in Connecticut, 0.23 million people. 0.08 million people is the increase in population for what? Maine. And 0.33 is an increase in population for New Hampshire. And 0.16 million, or 160,000 people, is the increase in population for Rhode Island. Okay, good. Let's say I call that something. Let's say I call that R. the vector we just got, let's call that R. L3. What do you think this is? Q, wait, why am I doing that? What if I say Q plus 2R? What do you think that's going to be? What do you think that means? If Q is a population in 2005, P is a population in 1995, and R is an increase from 2005, from 1995 to 2005, what is Q plus 2R going to be? What do you think it means? Don't give me numbers. Give me words.
What is that?
What does Q plus 2R mean?
So you have like 2 comma that period, that's much of that.
Right. So let's say that's my prediction for the population in, I don't know, 2015. It's going to be 2 of the same increments. All right. So my increments were 0.23, 0.08, 0.33, and 0.16. What do you think L2 plus 2 L3s is going to be? Let's make that L4. Let's take L2 plus 2 times L3, and let's store that as L4. And now let's do stat edit and take a look at the result. All right, so L2 is the population in 2005. L4 is my prediction for the population in 2015, which is taking the increase from 1995 to 2005 and doubling it. So if I double this, what do I get? 0.23 doubled is 0.46. If I add it to 3.51, do I get 3.97? Right? So isn't that what we're doing? Look, notice what we're doing. We're taking, all right, let's write down what we're doing. Let's write down here. All right, look, let's write, all right, I'm going to write it down. I'll get this out of there. This is what I'm saying. I'm saying let R, the increase, equal Q minus P. And we got for that 0.23, 0.08, 0.33, and point something. What the heck was it? 2, 3, 08, 3, 3, and 16? Okay, 16. So how do you do Q plus 2R? You do Q, which is the point, right, it's L1, but I'm going to do it on paper now. 3.51, comma, 1.32, comma, 6.40, comma, 1.31, and I'm going to add to it 2 times the increase, plus 2 times the increase, which was 0.23, comma, yeah, 0.08, comma, 0.33, comma, 0.16. So we're doing 2 things. We're adding these 2 vectors, Q and 2R, but to get 2R, a new vector, we have to dilate the R vector. So how do you dilate by 2? What does it mean 2 times 0.23, 0.08? What do you do? Multiply everything by 2. All right, so let's write that out. It's going to be 3.51, comma, 1.32, comma, 6.40, comma, 1.31, plus double R. Double R would be point what? 46, comma, point 16, comma, point 66, comma, point 32, and you can add all this up in your head. You don't need a Ziggy, but if you do, you're going to get the result we had in L4, all right? So what would that be? 3.97, is that right? Let's look at our L4. 3.97, perfect. And then 1.48, yep. And, whoa, where am I? What the heck happened there? I just lost my thing here. Hang on. it's going to be L2 plus 2 times L3. Right? Okay. So this one is 6.40 plus 0.66 is going to be 7.06. Yes, it is. And 1.31 plus 0.32 is 1.63. It is. Okay, perfect. So you don't need Ziggy to do this. The point is 2 times a vector dilates it, makes it twice as big, and then adding vectors, you add component-wise. The Connecticut's together, the New Hampshire's together, whatever. All right, so you can use vectors to signify all kinds of crazy stuff. All right, how about this one? No, I think we beat that into the ground. All right, I'm done with 12.3. All right, so 12.1 was how do you deal with vectors polar-wise? That's law of sines, law of cosines. 12.2 is what are the components? What are the horizontal, vertical components of a vector? 12.3 is what if you add, subtract, multiply, and divide them. And it doesn't have to be 2-dimensional, 3-dimensional, 4-dimensional. It could be any dimension you like. Now, 12.4 is about how do you multiply? How do you multiply vectors? Okay? So let's see how this works. Let's say all right, let me ask you this. You probably know how to do this already without thinking about it. All right, let's say I have, let's say I'm a car dealer and I'm selling cars, right? And let's say the consumption of cars, the vector C, is 22 cars of Model 1, 14 cars of Model 2, 8 cars of Model 3, 12 cars of Model 4, and 19 cars of Model 5. Okay. So that means I sold 22 cars of Model 1. I sold 14 cars of Model 2, and so forth in this month, let's say, right? Now let's say the price vector goes like this. Let's say the price of the cars is given as $19,000 for Model 1, $23,000 for Model 2, $40,000 for Model 3. Model 4 goes for $47,000, and Model 5 goes for $32,000. My question to you is, how much money did I bring in? What's my revenue? What would you do? Multiply 22 times 19, then add 14 times 23, 14 cars of Model 2 times $23,000 for that kind of car, plus 8 of Model 3 times $40,000 for that kind of car, and so forth. That's how you multiply vectors. That's called the dot product. The dot product of C dot P, called the dot product, is exactly what you just said. It's 22, let's write it out. It's 22 times 19 plus 14 times 23 plus 8 times 40 plus 12 times 47 plus 19 times 32. So how do you multiply vectors? You multiply them component-wise, right? You multiply, quote-unquote, the x's together, the y's together, the z's together, and so forth, right? But then you take those quantities and you add them up. So what you get, notice what we've done so far is when you add two vectors, you get a vector, right? When you subtract two vectors, you get a vector, right? When you multiply a vector by a constant, you dilate the vector, you get another vector. It's bigger. Okay. But when you multiply two vectors, do you get a vector? Is this a vector? 22 times 19 plus 14 plus 23. Isn't that a number? That's just a number. All right, let's see what it is. Let's get this number. It's 22 times 19. Let's see if I can do this. 22 times 19 plus 14 times 23. 14 times 23 plus 8 times 40. 8 times 40. Wait, where am I? I don't want to be here. through all this stuff. Let me start over. It's 22 times 19. So 22 cars times $19,000 per that kind of car, plus 14 cars times $23,000 for each of those cars, plus 8 cars times $40,000 for each of those cars. No wonder we only sold 8. Plus 12 cars times $47,000 per car, plus 19 cars times $32,000 per car, and you get a total revenue of $2,232. What are the units? 2,232 whats? Dollars? Really? You sold all these cars, you only made $2,000? It's in thousands, right? Because the 22, oh wait, where am I? The price thing, the 19 was in thousands of dollars. The 23 was in thousands of dollars per car. Then I multiply by car, I get thousands of dollars, right? So this is $2,232,000. Maybe I should say, well, let's write that. Times $1,000 is the units in thousands of dollars. So it's really millions, right? In dollars, that's $2,232,000, right, total? So that's an example of how you would multiply vectors. All right, so let's go. All right, let's try another one. Let's say we go to the population problem again. Let's say that P, population, is again, I'm gonna make like round figures, okay? 3 million in this state, 1 million in that state, because it takes forever to write these decimals. 6 million in this state, 2 million in that state, 1 million in that state, and 3 million in that state, let's say, okay? Now, let's say that I have another vector R, which is 7, 6, 5, 13, 9, and 6. And let's say that that's a percent increase for each of those states. So the first state that has 3 million people in it will have an increase, let's say this year, of 7%. The next state will have an increase of 6%. The next state will have an increase of 5%. Okay? My question to you is, what's R dot product times P? What does that mean, and how do you get it? You multiply component-wise. You do 3 times, well, it's 7%, so I should say 0.07. So 3 times 0.07 plus 1 times 0.06 plus 6 times 0.05. And what are you going to get? That total amount, what does that mean? That one, I'm going to get one number. That one number, what does it mean? Well, all right, let's calculate it first, and then we'll talk about what it means. So it's 3, whoops. Where's my thing? Here. It's 3 times 0.07 plus 1 times 0.06 plus 6 times 0.05 plus 2 times 0.13 plus 1 times 0.09 plus 3 times 0.06 gives you a total of 1.1. And what does that mean? 1.1 what? What 1.0 what? Cows? What is it? Well, it's 3 million people times 7%. It's 1 million people times 6%, and add it up. It's 6 million people times 5%. Add that up. It's actually the number of people. It's 1.1 million people increased population over all 6 states, like say the eastern seaboard or something. I don't know, the eastern states or whatever it is, the northeast states, whatever, right? So that's the net increase in 1 year of 1.1 million people for all those states combined. So 7% of 3 million, 6% of 1 million, 5% of 6 million, 13% of 2 million, 9% of 1 million, 6% of 3 million. Add it all up, net gain for all the states put together is 1.1 million people. All right, so I should probably say millions of peeps are the units there, right? Okay, so you know how to add vectors, you know how to subtract vectors, you know how to multiply vectors. Now, be careful, we're talking about only the dot product. Now, do you remember when you first learned your times tables, and they said, children, 2 times 3 is 6, children. Let's make a times table. Okay. Right? Remember those days? That was like first grade. When did you first learn, the X thing means multiply? But then in high school, it said, no. It's 2.3 is 6. We don't do that cross stuff. That's kindergarten. Right, dot? As it turns out, cross products and dot products are not the same. In this context, they are. When you multiply scalars, they are. But when you multiply vectors, they're not. So we talked about the dot product of vectors. We only talked about how to multiply vectors, the dot product. We didn't talk about the cross product of vectors. And the cross product of vectors, that's a complicated thing that we need 3 dimensions and matrices to talk about. And they're not doing a lot with matrices in this book, so I can't really talk about it. All right, but let's say, here's an example of where the dot product comes in. This comes up in physics a lot, by the way. The dot product is used a lot to figure out work, the concept of work, like foot-pounds. You ever calculate work in physics? No? And the cross product is torque. The torque vector is orthogonal to the other two. No. Okay, I'm not going to talk about it. But, all right, let's say, So, let's say I take this book, and I'm walking across the room with it. Am I doing any kind of work on it? No, not by physics definition. The definition of physics is if you're working against a force or a field, a gravitational field or something, right? If I'm moving this horizontally, I'm not working against any force. But, oh, damn it, I gotta pick it up now. Oh, jeez, it's heavy. I'm working against what? The force of gravity. All right, so that's work. That's how they define work in physics class, okay? So work is force times distance. That's it. That's all it is. All right. So if this thing, let's see, where am I? I lost my place. Okay. Let's say this book weighs, I don't know, 2 kilograms. Okay, 2 kilograms. And I moved it, I lifted it against the force of gravity, I don't know, 2 meters. Now let's make it interesting. 3 meters. Is the answer 6? The work that I did, is it 6? No, because force is not mass. Kilograms is a unit of mass. Force is mass times acceleration. You ever heard of Newton's 3 laws, right? F equals ma, right? Well, if a is the gravity, the acceleration due to gravity, I have to multiply by that. And what is the acceleration due to gravity? You know what? I need more room. Let's put it over here. Equals 2 kilograms times the acceleration due to gravity times 3 meters, let's say, okay? So what's the acceleration due to gravity? Force is mass times acceleration. Haven't we come across this before? No? 9 point, roughly. At sea level, on the Earth, something like 9.8, let's make round figures, 9.8. 9.8 meters per second per second. Now, don't say seconds squared, because that implies an area, and we don't measure area in seconds squared, okay? Acceleration is the rate of change of the velocity. If the velocity is in meters per second, we're talking about how many meters per second the velocity changes per second. So that's 9.8 meters per second, okay? It doesn't mean per second squared. All right, so what do you get? Well, what is 2 times 9.8? You can do that in your head, can't you? 19.6? Okay, so 19.6 kilogram meter per second per second. There's a name for that. Newton. Named after the guy who's got clonked on his head with an apple due to gravity. Okay, so newtons. Okay? Times your 3 meters. So now what do you get? What's 3 times 19.6? Go ahead. You can use a calculator if you have to.
About 50.
58.8, right. Okay, so it's 58.8 Newton meters. That's a unit of work, a unit of energy. Okay? Now that's if you're working directly straight against the force. Your displacement is parallel to the force. Okay, but that's not the definition of work. The definition of work is a scalar force vector dot displacement vector. It's a dot product of two vectors, okay? Now, as it turns out, the dot product, component-wise, is multiply the x's times the x's plus multiply the y's times the y's plus multiply the z's times the z's, right? Just like we did the dot product a minute ago. This is the dot product, right? Just 3 times 7 plus 1 times 6 plus, right? That's the dot product, yeah? The z direction, the k, yeah. Okay? But in polar form, it doesn't work out that way. In polar form, it works out this way. Work is the force vector times dot product, the displacement vector. But that's the magnitude of the force times the magnitude of the displacement times the cosine of the angle in between. Okay? So if you're doing this with law of sines, law of cosines, r theta stuff, okay, you can prove that the dot product works out to the force times the displacement times the angle in between, okay? Now, I'm not going to prove that here. I need matrices for that, so I'm not going to prove that here. But let's say, all right, let's say you're moving, let's think about this. All right, let's say you're moving a 350-pound refrigerator. Okay? Now, notice this notation. What does this look like? These lines, these vertical lines, what does that look like? Absolute value. The absolute value of a vector is the magnitude. It's the r. It's the r of, like the r theta, okay? Absolute value always means distance. When I say the absolute value of -5 is 5, I'm really saying that it's 5 units from yours. I'm not saying that it's to the left or to the right. That's what the negative is about. I'm just saying that it's 5 away. Right? So the magnitude of the vector, the length of the vector, that's the absolute value of the vector. Okay? So let's say I have let's see how we're going to put this. All right, so let's say I have a 350-pound refrigerator. And I want to move it 12 feet. But the angle that I'm, let me think about this. The angle that I'm working against, all right, let's put it this way. Let's say, okay, I have a 350-pound refrigerator, right? And I'm pulling at it. I'm pulling at it with like a rope, and it's taut. This rope is taut. Now, if I dragged it at 0 degrees, what's the cosine of 0? 1. So it's the same thing as 350 times 12. I'm done. Just like before when I did the weight of the book times the distance that I picked up the book, right? I was moving in the same direction. But let's say I'm not doing that. Let's say I'm not pulling it at 0 degrees. Let's say I'm pulling it at like 10 degrees. Is the full force, the force that I'm applying to this rope, am I using it efficiently? Am I using it all for dragging the refrigerator across the ground? No. At 10 degrees off, or even 80 degrees off the ground, whatever it is, there's a horizontal component of that force that's working. If I'm trying to drag it across the ground, I'm trying to move it horizontally, right? So let's say, really, with this again? So let's say I'm dragging this thing across the ground such that the rope is making, an 80-degree angle with the ground. Now what do you get? Well, 350 times 12, you can do that very easily, right? 10 times 350, 3,500. 2 times 350, 700. 3,500 and 700 is 4,200. But what's the cosine of 80? 4,200 times the cosine of 80. What is it? Well, let's find out. Use the calculator for that. It's not a reference angle, is it? The cosine of 80, I'm in degree mode, right? Yeah. So I can do 80 degrees if I want. So the cosine of 80 is much less than 1. So the horizontal component of the force is very little. Would you drag it? Would you say you had to do this job, and the force due to friction of dragging this refrigerator across the ground is 350 pounds. By the way, in the English system, pounds is a unit of force. I know that's weird. So would you pull it like this to drag it across? Would you pull it closer to a horizontal, like 10 degrees instead of 80 degrees? Right? If you pull it this way, it's going to be hard to drag it, right? If you pull it this way, it's going to be easier to drag it, right? So the 80 degrees is not smart, but this is what we get. Times 4,200 is 729 foot-pounds. Notice the units. Foot-pounds, okay? So it's 729 point, what? Point, what? 322? Okay. 322 foot-pounds. All right. But now think about it. What if I did 0 degrees? What does that mean? How does the rope look if I do 0 degrees with the ground? Straight down horizontal. So in other words, am I not using all the force I can possibly bear on the problem? The whole amount of force is going in the same direction that I want the refrigerator to go. I'm going to use the maximum amount of force, am I not? So because the cosine of 0 is 1. So you're going to get the full 4,200 foot-pounds. Now, what if I did it the other way? What if I went 90 degrees? I'm pulling it. I want to go there with this fridge, but I'm pulling it this way. What's going to happen? It's going to go there horizontally? No, because the cosine of 90 is 0. So you're doing no work. It's not doing any work. You're not producing any work. You're wasting your time. Right? So it has to do with the efficiency of work. Okay. All right, so that's the definition of work. It's the force vector, dot product, displacement vector, and you get a number, you don't get a vector. All right, so we're going to preview the homework in a minute. Let me just save this. All right, YouTube, that was nice knowing you. See you tomorrow.